In this video, we are going to look at application problems involving exponential growth. In word problems, you are going to set up equations, exponential equations. They're going to have the form y equals a, your base k, to the exponent x. When we graphed exponential functions, we discussed that the function is increasing when your base k is greater than 1. When the function is increasing, that is exponential growth. So the three questions we're going to look at today, the k, the base, is going to be greater than 1. There will be another video when k is between 0 and 1. The x, or the exponent on your base, is the number of time periods. That will become more clear what that means when we're actually doing the word problems. And then you have your base to the x and it's being multiplied by a. Looking through the lens of transformations, a represents the vertical stretch. Here in word problems, that is actually your initial value. So a is how much you start with. K is your growth factor, your exponential growth. And when you multiply those together, you get your value for y, which is the amount at the end after your number of time periods. So again, initially we have a value of a, and we can show that mathematically because initially means that time is 0, so there have been no time periods. Any base to the exponent 0 is equal to 1. So y is equal to a times 1, which is y is equal to a. So we are going to look at three problems, and each of the problems we need to first set up the exponential growth equation, and then we're going to use our equation to solve. So in the first question, we are told that Jennifer grew a colony of bacteria for a science project. Initially, there are 50 bacteria, and the population doubles every hour. So we are going to have an equation with x and y in it. We might use different variables depending that suit the situation a little bit better. So we are going to actually make a let statement. So here we are talking about the number of bacteria, and that is dependent on the number of hours. So we are going to say let B represent the number of bacteria. And then we also have the variable of time. So let T represent the number of hours. So I didn't use the letters X and Y, I used B and T, but it is good to keep in mind which one I replaced for X and which one I replaced for Y. So because the number of bacteria depends on the number of hours, your Y always depends on your X. So B depends on T, and what we say is that X is your independent variable, so T is our independent variable, and Y is the dependent variable, or B here. So I just made a little note of what I'm using for X and Y. In the question, you will always be given information to identify your A value and your K value. So here we are told there are initially 50 bacteria. So that's telling us our A value. So that's saying our A value is 50. And then we are told that the population doubles every hour. So that tells us our K value is 2. So therefore, we want to set up our equation. So the general form is y equals a k to the x. So here we are using b for y. A is 50, k is 2, and that is to the exponent t. And that is the equation for the first problem. Now in part B, we are going to use that equation. We are asked how many bacteria are there after 6.5 hours. So I am going to substitute 6.5 in for the time. So I'll highlight that. And then we just type that into the calculator. 50 times base 2 to the exponent 6.5. Remember that exponent is just on the 2, so it's not 100 to the exponent 6.5. And you should get 4,525.48. So I'm going to round that to 4,525. So after 6.5 hours, there are that many bacteria. Just a note about using your calculator. To make this an exponent of 6.5, you should all know where your squared button is, even your cubed button. You're not used to writing or solving with different exponents. So some of the buttons that you could be looking for in your calculator is the little hat. You could be looking for the x to the y, or you could be looking for x to the little box. So now we're ready to look at the second question. Here we are told the population growth of the Golden Horseshoe area around Lake Ontario is among the fastest in Canada at an estimated 1.84% per year. The population according to the census is 11.5 million. So again, I need to use let statements to define my variables. So I have let P represent the population in millions because the population is 11.5 million, and T represents the number of years. So it's good to identify the independent and dependent variables. Because the population depends on time, that means the population is your dependent variable, so y, and your independent variable is time. So now we need to identify how the function is growing and the initial value. So we are told that it is growing at 1.84% per year, and that the initial value is 11.5. So A is 11.5 because we defined our population in millions. However, K is not simply 1.84. When you are given a percentage, you need to change that to a decimal. So 1.84 divided by 100 is 0.0184. Remember, dividing by 100, the decimal is between the 1 and the 8. You have to move 2 to the left. So then it's 0 decimal. You have to add that 0.184. We know this is growing because you were told in the question, the population is growing. So if we just have a k value of 0.0184, that's actually less than 1, which means a decay. So what you need to do is you need to take the percentage that it's growing by and you have to add it to 1. Basically, this 1 means 100%. So you're keeping 100% of the population you have now, and then you're adding an additional 1.84%. So really, you are at 101.84% of the previous population. That's how much it's growing by each year, but we change that to a decimal. So that's 1.0184. So that is the k value that we are going to use in the equation. So the equation we get is P is equal to the A value, 11.5, times the base, 1.0184, to the exponent T. And then part B, we are asked, what is the population in 10 years? So now we are going to substitute in 10 for the exponents and then use our calculators. And you should get 13.8 million. So after 10 years, the population will reach 13.8 million people. In question 3, we are told that bacteria doubles every 15 minutes in favorable conditions. There were 100 bacteria cells at noon. So here I define my let statements as B, which represents the number of bacteria, and T represents the number of 15 minutes, because this information here about the bacteria doubling every 15 minutes is really important and changes this question from the first question. Because in the first question we looked at, the bacteria doubled every hour. So T represented the number of hours there. Here, T represents the number of 15 minutes. So basically the number of times that the bacteria doubles. So here again, bacteria is the Y as it depends on your time, which is X. So now let's identify the A value. That's the initial value. So we're initially starting with 100 bacteria. So A is 100. And then the K value, the growth, is your doubling. So that means K is equal to 2. Doubling means you are increasing by 200%. So really that's 200%. 200% divided by 100 is equal to 2. So really when you have that k value of 2, you are changing that percentage to a decimal number. So your equation then becomes B is equal to the A value of 100 times your growth factor, which is 2, to the exponent T. So now we are asked how many cells would there be by 3 p.m. So we want to know the number of bacteria, and then we have to substitute in time. So time is not equal to 3. So you might be tempted to do that, but that's actually not correct. even though we are starting with 100 bacteria at noon and we want to know how many there are 3 hours later, because the bacteria doesn't double once per hour, it doubles once every 15 minutes. So we need to know how many times bacteria doubles within the 3 hours. So within 1 hour, there are four 15-minute blocks. So within 1 hour, the bacteria doubles 4 times. So within 3 hours, it is doubling 12 times. So now the equation will be b equals 2 to the exponent 12, and then put that into the calculator. So after 3 hours, or 12 doubling time periods, the bacteria will reach 409,600.